Hello dear students, myself Mihir Mistry from Mechanical Department of LG Institute of Engineering and Technology. So today we are going to discuss Reynolds apparatus. So let's start the practical session. So aim of our practical session is to study different types of flow or visualize different types of flow, right? So we know that there are different types of flow, for example laminar flow, turbulent flow and transition flow. Now, how can you distinguish them? So, laminar flow, you might be aware that the pattern of flow will be very organized. That means, fluid particles will be flowing in a very organized manner, right? That is known as laminar flow, right? Mathematically, for the laminar flow, Reynolds number will fall below 2000, right? Same way for turbulent flow, the fluid particles will not be having any linear motion. They will be having disturbing motion, right? Zigzag manner. So for that kind of flow, it will be known as turbulent flow. And mathematically, for turbulent flow, the Reynolds number will fall greater than 4000, right? For transition flow, the value will fall between 2000 and 4000 for the Reynolds number, right? So here, what we will do today, we will experiment one thing, that is, we will visualize the laminar pattern, we will visualize the turbulent pattern, and then we will identify and prove that yes, the visualized laminar pattern is mathematically is also correct, and yes, the visualized turbulent pattern is mathematically correct. Okay, so this is our experimental setup. Now let's start the experiment. Hello students, so this is the experimental setup for visualization of laminar flow, turbulent flow and transition flow. So let us understand the components of experimental setup. So first of all, as you can see, this is the reservoir tank. In this reservoir tank, a pump submerged, that is submersible pump, that pump is submerged. So when we will turn on this pump, it will fetch the water from this reservoir, and through this particular pipeline, it will supply the water to this overhead tank. In this overhead tank, the water will get accumulated. The water further will be supplied from this overhead tank to this transparent glass tube, right? And in the middle of the transparent glass tube, as you can see, one needle is provided, right? Through this needle, we will supply the ink. So it will be help us to visualize the laminar flow or turbulent flow. You can see that the needle is connected to this dye tank that is located at this top. So we have to supply or pour the dye inside it before the experimentation starts, right? Now further, let's come back to this section. So this is the glass tube. Glass tube is going downward side, and through that it is connected to this particular valve, right? This is the outlet valve, right? So what will happen? As soon as we will open this valve, the discharge will start. You can see that the discharge is occurring. So we will measure the actual discharge through that particular outlet, right? One more thing, that is here, as you can see, this is the bypass pipe, right? The function of the bypass pipe is to avoid the overflow in this particular overhead tank, right? So at this particular level, the bypass pipe is fitted. So if the water level rise above this particular level, then the bypass pipe will be activated and the excess water will be supplied back to the discharge tank, right? So this is how the water flow or water path of the experimental setup will work. Now let's start the reading. Now I will open the valve slightly, that is provided at the bottom. So the water flow will occur through this pipe. So initially the valve is opened very partially, that means the velocity is very low, and low velocity means low Reynolds number, and that means the laminar flow, right? So now in order to visualize the flow pattern of this particular flow, what I will do, I will open the ink supply. Now just observe the needle. Now the ink is supplied. Now as you can see, the ink is going straight downward, right? That means the supply right now is laminar flow, right? That means all the molecules in this pipe section are going or moving in a straight downward direction. So that is the real life visualization of laminar flow. Now we have to prove this mathematically also. right? So that we have to find out Reynolds number, and that Reynolds number should fall below 2000. So let's check that. So for the mathematical proof of the laminar flow, we have to find out the Reynolds number. So Reynolds number is equal to Re is equal to rho Vd by mu, where rho is the density of the given fluid that is known to us, right? D is the diameter of the pipe section, right? That is known to us, and mu is the dynamic viscosity of the fluid that is also known to us. So only unknown is velocity, that is actual velocity. So for finding out the velocity, we should find out the discharge first. So you know that discharge Q is equal to area into velocity. So if you make V as the subject, that is velocity as the subject, then V is equal to Q by A, right? So first of all, we have to find out the discharge. So let's find out the discharge. Now let us measure the actual discharge. So this is the beaker. I will start the reading at 200 ml in the stopwatch. So I have started the stopwatch. And I will stop the stopwatch at 600 ml. Right, then for the actual discharge, the interval of the discharge is 400 ml and the time taken is around 24.45 seconds. Visualization of turbulent flow. So for that, first of all, I will open the ink supply. So this is the ink supply. You can see right now the flow is nearly laminar, right? Now the valve will be opened, so this will be turbulent flow, right? Zigzag fashion of the ink. Right now this is the real visualization of turbulent flow. I hope you can see the ink is moving in the zigzag fashion, right? So now we have to prove that mathematically also, right? So we have to find out the Reynolds number, and that should fall greater than 4000. Now the discharge. So I will start the interval from 200 ml. Start. Stop. So you can see only 3 seconds for the interval of 400 ml. So in the experiment you might have learned that the only value that you are supposed to measure is discharge, right? And time required for that discharge, right? So that means you are supposed to find out the interval, that is, let's say you will start the stopwatch at 200 ml, you will stop the stopwatch at 600 ml. So the interval you have to decide, that is 400 ml. And for that interval, how much time has been noted, right? So you are supposed to record the time only, okay? And also you have to operate the valve in order to make the discharge, right? Now after the experiment, you might be aware that you should note the time required to do the discharge for the given arbitrary value of the volume, right? Say here in our example, the arbitrary value was from 200 ml to 600 ml. That means the interval for the volume was taken as 400 ml, right? So that 400 ml, how much time is noted, that you have to measure, okay? Now calculation part. So as we can see on the screen, for laminar flow, we might be aware that for visualization perspective, the flow will be in pure linear motion, right? So let's practically prove that also. So its Reynolds number should fall below 2000. Okay, so let's start. So as you can see in the given data, D is the internal diameter, that is 25 mm, or you can say 0.025 meter. Rho, that is the density of the given fluid, that is 1000 kg per meter cube. Then mu, that is dynamic viscosity of the water at 40 degrees Celsius, that is 0.657 into 10 raised to minus 3, right? So if the temperature will change, then the dynamic viscosity of the water will also change. You should take note of the same, right? Now standard conversion of volume is given, that is 1 meter cube is equal to 1000 liter. That will be used later on. Okay, we know that the interval that we have taken for the volume is 400 ml, so that is nothing but 0.4 liter. So that will be equivalent to 0.0004 meter cube of volume. Okay, now we know that Reynolds number is what? Rho Vd divided by mu. In that equation, we know we do have the value of rho, we do have the value of d, we do have the value of mu. So only unknown value is what? V. So for V, we should first find out the Q, because you know that Q actual is equal to what? Cross section area into actual velocity. If you make V as the subject, then it will be Q actual divided by cross section area, right? Now, cross section area can be found out using the given diameter, that is pi by 4 d square, right? So the given diameter, according to that, the cross section area will be 0.49 into 10 raised to minus 3 meter square, right? Same way, now discharge. So for discharge, we know the interval, that is 400 ml, that volume we have taken. So if you convert it into meter cube, so that will be 0.0004 divided by time taken for the same, that is 25.45 seconds. So if you will do the division, then the final value will be 1.57 into 10 raised to minus 5 meter cube per second, right? So that is our Q actual. We do have the Q actual, we do have the area of cross section, then we can find out the actual velocity. So actual velocity will be nothing but 0.032 meter per second. Now, let's put this value in our Reynolds number equation. So if you will do so, so the final value of the Reynolds number will be 1219. And remember, it is a unitless quantity. Okay, so this is how it is proved that the flow which we have visualized earlier in the experiment, that is in linear motion, so that is nothing but laminar flow. Okay, so it is proved here mathematical also. Now, for the calculation of turbulent flow, given data is there on the screen, that is diameter is 0.025 meter, density of the fluid is 1000 kg per meter cube, mu, that is dynamic viscosity at 40 degrees Celsius, that is equivalent to 0.657 into 10 raised to minus 3 Newton second per meter square, right? Then standard conversion for volume is given, 1 meter cube is equal to 1000 liter. Our interval that we have taken for the volume, that is 400 ml, so it will convert it into meter cube as 0.0004 meter cube. Now, Reynolds number is again rho v d by mu. We do have the value of rho, d and mu, so we are supposed to find out only v. Let's repeat the same procedure. Okay, so that is discharge is equal to area into velocity, make v as the subject, so it will be discharge upon area, find out the area from the given diameter, then find out the discharge. So discharge value will be 1.33 into 10 raised to minus 4 meter square per second. Now, from that, the actual velocity will be 0.271 meter per second. So substitute the value of velocity in the Reynolds number equation. So the Reynolds number will be equivalent to 10,341. Now student, you might be able to appreciate that you have seen the flow. So that was purely zigzag, and for that turbulent flow, we have proved that the mathematically Reynolds number is falling greater than 4000, right? That is 10,341, right? So what is our conclusion? Our conclusion is very simple, right? As you can see on the screen, so for laminar flow, that is a linear motion, our Reynolds number will be less than equal to 2000, and for turbulent flow, the same will be greater than equal to 4000, right? And the particular values are given over here. Okay, so thank you.